Maybe you're new to Barotrauma, and this whole electrical engineering thing is really new and you'd like to learn more. Maybe you're sick and tired of walking into a hallway filled with broken junction boxes. Or maybe you'd like to see a reactor that can handle 4 fulgurium fuel rods and a drunken captain. Either way, you've come to the right place. Welcome to my video on perfecting reactor control. Now, this is probably going to be quite boring, and it will definitely be quite dry and repetitive. But I can promise you, whether you are a beginner or an advanced engineer in barotrauma, by the end of this video you will have all the tools you need to construct the ideal reactor controller. Understanding reactor control starts with understanding reactor dynamics. And in this respect, barotrauma is relatively true to life. Fuel rods create fission. Fission creates heat. Heat creates steam. And steam is used to create energy. Different types of fuel produce different rates of fission. The fission rate determines the rate of energy production yielded from the reactor. There are 3 forms of fuel available: uranium, thorium, and fulgurium. There are 2 differences in the various forms of fuel. One is the power rating. In barotrauma, the power rating of a fuel rod describes a maximum achievable reactor output from a single fuel rod. For example, a uranium fuel rod has a power rating of 80. This means that at 100% fission rate, a single fuel rod of uranium can produce 80% of the reactor's maximum power. A thorium fuel rod has a power rating of 100, and a fulgurium fuel rod has a power rating of 150. The other factor that varies between the different types of fuel is durability. Durability points are consumed at a constant rate that is fixed dependent on the reactor. Keep in mind, this is independent of the rate of energy that is produced or consumed. Uranium fuel rods have 100 durability points. Thorium rods have 200, and fulgurium rods have only 150. Combined with the amount and type of fuel in the reactor, the fission rate determines how fast energy is produced internally. The turbine output determines how fast that energy is converted into electricity. This is where the balance lies in reactor control. Production must match consumption. If the rate of energy consumption exceeds the rate of energy production, there isn't enough electricity to go around. You can hear the engine start to decline, lights will begin to flicker, and eventually everything will go dark when there is insufficient power. If energy production exceeds energy consumption, the heat that is produced by fission is not removed from the reactor, and reactor temperature begins to rise. This can result in a very bad day. In small amounts, energy overproduction causes overvoltage, which will cause slow but gradual damage to junction boxes and other electrical components. Precise reactor control not only prevents fires and meltdown, but also reduces the need for repair across the ship. This is your basic reactor interface. Here are the 4 slots in which fuel rods can be placed, and this gauge displays the current fission rate. This gauge shows the current turbine output, and this bar graph displays the current reactor temperature. These 2 sliders allow you to manipulate the fission rate and turbine output set points. This graph shows the recent history of both power production, shown in orange, and power demand, shown in white. And here we have the power off button for the reactor. It is important to use this when docked so that fuel rods aren't consumed unnecessarily. If you have a screwdriver equipped and you press E instead of double-clicking on the reactor, you will access the connection panel, shown here. On the left are the inputs. These allow the reactor to be shut down remotely or allow for the fission rate and turbine outputs to be controlled through wiring. On the right side are the outputs. The first, the power output marked in red, is a high voltage connection which is used to connect the power produced from the reactor to the junction boxes distributing power to the rest of the ship. The other connections, such as temperature, power, and load outputs, can be used to monitor reactor performance. In order to construct the parts that we need for the reactor controller, you're going to need to craft a few components. Thankfully, all the recipes are quite simple. Every component that we need can be crafted from an FPGA circuit and tin. It is important to note that any electronic component is made from these parts and can be deconstructed into the component parts and refabricated into any other component. We will need a few switches, which can be crafted from FPGA circuits and plastic, and the FPGA circuits themselves can be crafted from copper and plastic. You will need an ample supply of wires, which are crafted from copper and rubber and produced 5 units at a time. Now let's talk about the basics of wiring. You do not need to have a tool equipped to place components. Simply double-click on the component itself in your toolbar to activate it, hold right-click to show the placement grid, hover over where you would like the component to be placed, and left-click to place it. You do, however, need to have a screwdriver equipped to place and remove wires, and you will need to have a wrench equipped in order to detach components. Wired connections in Barotrauma are analog, meaning that they can conduct signals that vary in strength. However, many components have inputs or outputs that behave in a digital fashion. That is, instead of being 1 or 0, they respond to signals that are either 0 or anything other than 0. I want to take a second to discuss the difference between a button and a switch. Here, on the left, we have a switch. On the right is a button. On the first click, the switch would go from an off to an on state, and would stay there until I clicked it again. Then it stays off until I click it a third time, where it goes back to the on state. The button, on the other hand, goes from the off to the on state and immediately back to the off state without needing to be pressed a second time. It does this every time the button is pressed. This might seem like a minor difference, but in the game, this is an important concept referred to as toggle and pulse. Once again, using the screwdriver to show the connection panel for either one of these components reveals that they both only have a single port, labeled signal out. This reveals another important concept in wiring in Barotrauma. There are ports that are input and ports that are outputs, but never ports that are both. And this brings us to the underappreciated memory component. Looking at the connection panel for this component reveals that there is an input port, an output port, and a locked state port. The input port receives signals and stores the last signal that was received. The output port constantly streams the most recently stored value. However, the locked state port can be used to hold a value in memory. So long as a non-zero signal is received by the locked state port, the value stored will not change regardless of the signals received by the input port. The memory component can be combined with mathematical components in order to manipulate received signals. Most math components have 3 ports, an input 1, input 2, and a signal out. Their function can be considered as a small equation, a minus b, a plus b, a times b, a divided by b, and a to the power of b. The last 2 components that are relevant to this discussion are the signal delay and signal inversion components. As its name implies, the delay component takes a received signal and delays it a fixed period of time. It is important to note that it ignores all other signals during this wait time. The signal inversion component, on the other hand, takes any signal and converts it to 0, and converts a 0 or no signal to 1. In both cases, the connection panels are the same, an input port and an output port for the modified signal. While each of these components seems very simple, when combined they can have very powerful effects. Consider the combination of a memory component and a multiplier component. Once a component is placed, it can be manually edited to contain any value that we want. By connecting the output of the memory component to one of the inputs of the multiplier component, we can amplify or attenuate the input signal by any factor that we should choose. One subtle but powerful detail about math components in Barotrauma is that most of them can be clamped to a specific output range. In this example, if we were to clamp the limits of our multiplier from 10 to minus 10, then regardless of what the input could be, it will never be higher than 10 or lower than minus 10. Wi-Fi components can be used to transmit signals long distances, up to 20 meters. Looking at their connection panel reveals an input and an output port. Although there is a port that allows the channel to be determined dynamically, it is easiest just to set the Wi-Fi channel manually once these components are placed. Signals going into a Wi-Fi component are broadcast to all other components on the same channel. Signals received by these components are then streamed through the signal out port. The relay is another powerful component, allowing signals for 2 channels to be connected or disconnected simultaneously. Looking at the relay connection panel, we see that there is 1 high voltage channel and 2 low voltage channels. Once again, it is important to acknowledge that these signals only travel in one direction. Input cannot be received through an output port. Once placed, relays are on by default and will not turn off until commanded to do so. This can be achieved by sending a 0 signal through the set state port or a non-zero signal through the toggle state port. The current state of the relay can be read from the state out port. If it is on, the state will be 1, otherwise it will be 0. And last but not least, we have the oscillator component. Looking at the connection panel of the oscillator component, we see that there is a set frequency port, a set output type port, and a signal out port. While it can also be set manually, the frequency of the oscillating signal can be configured dynamically through the set frequency port. While it can be configured to send a sine wave or square wave, the oscillator will produce a pulsed signal by default. The first step in constructing our automatic reactor controller is to build a 5-channel Wi-Fi switch, which we can use to connect and disconnect the controller. The use of Wi-Fi components instead of relays allows for the majority of the circuitry to be relocated either due to convenience or for security reasons. For this part, you'll require 5 Wi-Fi components, 3 relay components, 1 switch, and 13 wires. While the components can be placed in any arrangement that you like, I would suggest arranging them like this for simplicity's sake. Put them near your reactor. Once the components have been placed, assign them to channels 1 through 5 as shown here. Now, while you won't be able to see all the connection panels at the same type as I have shown here, this is the easiest format that I could think of to show how the wiring must be performed. Start by wiring the signal out of the switch to the set state input for each of the 3 relays. Then, wire the signal out from channel 1 of the first relay to the signal input of the first Wi-Fi component. Wire the signal in of the second channel on the first relay to the signal out of the second Wi-Fi component. Wire the signal out of the first channel of the second relay to the signal in of the third Wi-Fi component. Similarly, wire the signal out of the second channel of the second relay to the signal in of the fourth Wi-Fi component. Finally, wire this input of the first channel on the third relay to the output of the fifth Wi-Fi component. Connect the input of the first channel of the first relay to the temperature out port on your reactor. Connect the output of the second channel of the first relay to the set fission rate input of your reactor. Connect the input of the first channel of the second relay to the power out channel of your reactor. And connect the input of the second channel on the second relay to the load out port of the reactor. Finally, connect the output of the first channel of the third relay to the set turbine output port on the reactor. If you've wired everything correctly, you should now have a switch that allows you to connect and disconnect the temperature, power, and load output signals, as well as the fission rate and turbine output control signals from your reactor to their own respective Wi-Fi channels. The 5-channel Wi-Fi switch is just one of a handful of subassemblies which must be understood before we put together our reactor controller. The next on the list is the system clock. Now, this might seem like a slightly more complicated oscillator circuit, and you'd be right, but I do it this way to simplify the mathematics later on. Here, we use a static memory cell to define the time interval, also called the period, an exponentiation component raised to the power of -1, which calculates the reciprocal of period, also called frequency, and an oscillator component, which takes that frequency and generates pulses at the desired rate. The connections here are straightforward. We connect the signal out of our memory component to the signal in of our exponentiation component. Then we connect the signal out of the exponentiation component to the frequency input of the oscillator component. If you've wired everything correctly, you should now be able to control the frequency of the clock signal by defining the time interval between pulses. So far, we've only used memory components to save static values that are entered manually. Let's build a dynamic memory cell. This will require a delay component, an inversion or not component, a relay component, and a memory component. We'll use the memory component for storage, the relay component as the bus to determine where the information comes from, and the remaining components to determine when the data is saved. Wiring the dynamic memory cell begins by connecting the output of the first channel of the relay to the input of the memory component. Then connect the state out port of the relay to the input signal for the delay component and connect the output port of the delay component to the toggle state input of the relay. Make a second connection from the state out port of the relay to the input of the not component and from the output of the not component to the lock state port on the memory component. The dynamic memory cell is now ready for use. Connect the data that you would like stored to the input of the first channel of the relay. If you've wired everything correctly, here's how it works. The data is held in memory in a lock state until a signal is received from the clock. When the signal is received, the input is connected to the memory only for a brief second before the relay is opened again, and the memory is relocked. Sometimes we don't want a system to be working as fast as possible, but only as fast as we want it to. Discretizing is the process of taking a smooth signal and breaking it into chunks that only change as often as we'd like. All that's needed for discretization here is a delay component. The delay component's ability to hold its output constant while waiting before changing to the next input value is what performs the bulk of our discretization. In fancy terms, this is called a zero-order hold. We now have everything we need to move on to the next step, building the temperature controller. The control loop is simple. Measure the reactor temperature, calculate the adjusted fission rate, apply the new fission rate, and see if our reactor temperature has changed. To build the temperature controller, you're going to need 9 memory components, 5 multiplication components, 3 addition components, 3 delay components, 2 division components, 2 Wi-Fi components, 1 subtraction, exponentiation, oscillator, and relay components, and 34 wires. Ready? Here we go. This is how I would recommend laying out the components. It's not necessary, but for organization's sake, it makes sense to me. Before you decide it's too complicated, let's break it into pieces. See these? These are Wi-Fi components. Simple enough, we know what these do. You might recognize these blocks as the system clock. These are all static values being applied mathematically to the input signals. This is a dynamic memory cell. These are more basic mathematical manipulations of the signal. And these are simply discretization blocks. Let's begin by configuring our components. The Wi-Fi component on the left should be configured for channel 1. The one on the right should be configured for channel 2. The exponentiation component should be configured for a fixed value of -1, and the addition component on the far right should be clamped between values of 100 and 0. All the delay components should be configured for a fixed value of 0.05 seconds, and all 3 of these memory components should be configured for the same value of 0.05. This memory component should be configured for a value of 100, while the one beside it should be configured for a value of 50. The next 3 values are most important and will be referred to later. The first one is called Kp, or your proportional gain. It should be configured for a value of 1. The second is Ki, or your integral gain. This should be configured for a value of 0.2. The last memory component will hold Kd, or your derivative gain. This should be set for a value of 0.3. Before you start the wiring, I recommend that you ask your crewmates to leave you uninterrupted if possible. It's much easier if this is performed all in one shot. Then, connect the state output of the same relay to the input of the delay component immediately above it. Connect the output of this delay component to the toggle port of the relay. Then, make a connection from the state output of the relay to the input port of the NOT component above it and to the right. That's it for the dynamic memory cell. Let's move to the system clock. Starting from the memory cell in the top left, make a connection from its output port to the input port of the exponentiation component to the right. Then connect the output of the exponentiation component to the set frequency port of the oscillator. Finally, connect the output of the oscillator to the toggle port of the relay that we were working on earlier. That's it for the system clock. Now let's make connections between the static memory values and their associated mathematical components. Connect the output port of the memory component to the first input port of the mathematical component immediately below them. Here, 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 and here. Connect the output of the left-hand Wi-Fi component to the second input of the mathematical component to its right, and the output of that mathematical component to the second input of this next mathematical component to its right. Connect the output of that mathematical block to the input of the delay component to its right, and the output of that delay component to the remaining inputs of the blocks shown here, here, and here. Connect the output of the uppermost multiplication component to the first input of the addition component shown here. Then connect the output of the multiplication component shown here to the input of the addition component to its right. Connect the output of this addition component to the input of our dynamic memory, and the output of the dynamic memory to the remaining input of the same addition component. Make another connection from the output of that addition component to the input of the multiplication component to its right, and from the output of this multiplication component to the remaining input of the addition component beside it. Now connect the output of this addition component to the first input of the addition component to its right. Now connect the output of the lowest delay component to the second input of the subtraction component to its right. Connect the output of this multiplication component to the last addition component on the right, and finally, from the output of this addition component to the input of the Wi-Fi component immediately above it. If you've wired everything correctly, here's how it works. I'm just kidding, I'm not going to explain all this. This is basically what we call a proportional integral derivative controller. And if you're interested in learning more about how it works, there are plenty of websites that have lots of articles on PID control theory. It's time to build the last component of a reactor controller, the turbine control. For this part, you'll need 3 memory components, 3 Wi-Fi components, 3 multiplication components, 2 division components, 2 delay components, a subtraction component, an addition component, and 17 wires. Once again, you don't have to lay out your components like this, but I believe this is probably the simplest layout that I can think of. Let's start configuring our components. This Wi-Fi component should be configured for channel 3, this one for channel 4, and this one for channel 5. This memory component should be configured with a value that matches the maximum power output of your reactor. If you're not sure what that is, open up your submarine in the submarine editor and double-click on the reactor. The maximum power should be among the first values listed. This memory component should be configured for a value of 100, and this one configured for a value of 10. Finally, these 2 delay components should be configured for values of 0.02 seconds. Begin the wiring by connecting the output of the upper left Wi-Fi component to the second input of the subtraction component to its right. Then, connect the output of the top right Wi-Fi component to the first input of the same subtraction component. Make another connection from the output of the top right Wi-Fi component to the input of the delay component immediately below it. Similarly, make a connection from the output of the top subtraction component to the first input of the division component below it. Connect the second input of this division component to the output of the memory component to its left. Connect the output of this division component to the first input of the multiplication component below it, and the second input of this multiplication component to the output of the memory component to its left. Make a connection from the output of this multiplication component to the input of the delay component below it, and from the output of this delay component to the first input of the multiplication component below that. Connect the second input of this multiplication component to the output of the memory component to its left, and the output of that multiplication component to the second input of the addition component to the right. Now, going back to the uppermost delay component, connect its output to the first input of the division component below it. Connect the output of that division component to the input of the multiplication component below it, and the output from that multiplication component to the first input of the addition component below that. Make another connection from the output of the memory component on the top left to the second input of the division component on the right. Finally, make a connection from the output of the addition component to the input of the lower Wi-Fi component. If you've wired everything correctly, you will have created what's called a feed-forward controller. Operation of this controller is relatively simple. You can connect or disconnect it from the reactor through the 5-channel Wi-Fi switch, and beyond that, the controller pretty much takes care of itself. This controller should be able to handle anything you can throw at it. However, to give it the best chances of success, always start up under a steady load and keep the reactor as loaded as possible. This includes putting 4 fulgurium fuel rods in it, although it might overheat for a few seconds before recovering. Congratulations! If we've both done our jobs right, you should now have an accurate, precise, and powerful automated reactor control system. I know it was a long slog to get through these instructions, but I hope it's worth it. Have a great time and enjoy Barotrauma.